G'day, let us conclude our current unit of hydrocarbons by today having a look at some further reactions of the alkenes, specifically oxidation and polymerization. Lesson objective, we're going to understand oxidation and addition polymerization reactions with alkenes and describe the use and pollution of plastics. Learning outcomes as always below there. Reactions of the alkenes. So we started this in the previous lesson where we looked at addition, reaction with electrophiles and the mechanism thereof. Let's continue it now by, as I said before, looking at oxidation and polymerization reactions. In general, an oxidation reaction is the addition of an oxygen atom or the removal of hydrogen atoms from a molecule. We can consider the atoms we're adding or taking off when we're in the organic chemistry side of it. In the physical chemistry side, we've got our movement of electrons, oxidation and reduction as loss and gain respectively. And that is all still true. It's just we're looking at what the atoms are doing this time as opposed to what the electrons are doing. We use the symbol bracket O bracket to represent an oxidizing agent or bracket H bracket to represent a reducing agent. This just helps us simplify the equation a little bit. Then our polymerization reaction, something we haven't looked at before. This is where we combine relatively small repeating units called unit molecules called monomers into large polymer molecules, macromolecules. So we take a repeating unit that's the monomer, and then we react many of them together and we get a long macromolecule called a polymer made up of these many repeating units. But let's first start with our oxidation reaction, oxidation of the alkenes. Oxidation is the addition of oxygen, or defined as the removal of hydrogen. So we could form a number of possible functional groups when adding oxygen to an alkene. These include alcohols. So we could have an alcohol group there. I don't know, we just have some sort of molecule like that. We could have aldehydes, where aldehydes we have a carbonyl, double bond O with a H at the end of the molecule, the rest of the molecule there are aldehydes. Carboxylic acids, similar. They're a sort of combination of the two, where we've got the carbonyl group and the hydroxyl group, the rest of our molecule. And then our ketones have the carbonyl group in the molecule, like so. So alcohols, aldehydes, carboxylic acids, and ketones. So it all very much depends on where the alkene is positioned. Is it at the start of the molecule? Is it in the molecule? How many carbons are bonded to the carbons that are in the alkene? Lots of different variables, and as a result, we will get a number of different species, possibly, that has oxygen. Organic molecules can be oxidized by oxidizing agents. So oxidizing agents are species that provide the oxidation for our reactant. They themselves are reduced. So in this case, they are providing the source of the oxygen atom, or conversely, they are taking the hydrogen atom off of the molecule. But if we think about them containing oxygen atoms for one example, and if they are providing that to the other molecule in order for that to become oxidized, well, they themselves are losing that oxygen, so they themselves are reduced. Oxidizing agents are reduced, and reducing agents are oxidized. So we utilize a number of them in organic chemistry, so we need to be able to identify certain species as oxidizing agents. And we denote them in an overall equation by just O. So we're just interested in where this source of oxygen is, where this oxygen atom is going. So one such oxidizing agent is acidified potassium manganate, and we can oxidize our alkenes using this. So we might represent it like this, H plus being our source of acid, whatever acid that is. Brosylate acid, just a H plus donor, so that's our source of hydrogen. And then our potassium permanganate, KMNO4. So K plus and MnO4 minus. The product of the oxidation will depend on the reaction condition. From our learning outcomes, there are two we need to be familiar with. Oxidation by cold dilute acidified manganate ions to form the diol, and then oxidation by hot concentrated acidified manganate ions leading to the rupture of the carbon-carbon double bond in order to determine the position of alkene linkages in larger molecules. So depending on the harshness of our reaction conditions, will dictate whether we are completely severing that alkene bond, completely breaking the carbon-carbon double bond, or if it's not harsh, then we will just be making the diol. The diol being similar to an alcohol, only di meaning two, we've got two alcohols on our molecule. You know, you could have a triol with three alcohols. So I don't know, if we have a diol like this, we have a molecule with two, let's just do that, with two alcohol groups, thus a diol. So let's look at both of these. Let's consider first the unharsh conditions. So unharsh, it's a low temperature cold and it's not concentrated. So both of these have the same oxidizing agent. We're just changing the temperature and we're changing the concentration. So the unharsh conditions, cold and dilute, we form the diol. Oxidation via cold dilute acidified manganate solution. Can consider cold and dilute as not being harsh conditions, as I say. So we will not rupture the C double bond C in this instance, rather we'll convert the alkene into the diol. It adds two alcohol groups to each carbon of the alkene. The source of the hydroxyl group comes from water and the oxidizing agent. So we're just going to represent that with our bracket O in the equation. Let us consider this here. So let's say if I had a alkene such as ethene, and we were doing the cold dilute reaction conditions. So we said that the source of oxygen comes from water and our oxidizing agent. So let's show that. Let's show our water and let's show our oxidizing agent. So if we're adding a diol, we're adding two oxygen atoms essentially. So we've got an oxygen atom there, oxygen atom there. This is our acidified potassium manganate. So we have reaction conditions. I'll do this down here because I'm running out of space to do it on the same line. We have cold and dilute acidified potassium manganate. So we form a diol. We don't have harsh enough conditions to completely sever that. Rather, we can break one of the bonds and we put a hydroxyl on one carbon and a hydroxyl on the other carbon. And we form ethene 1,2 diol, showing that the hydroxyls are on carbon 1 and carbon 2 respectively. So that's our first instance of oxidation of an alkene, cold and dilute to form the diol. Now we can see this reaction is occurring because our manganate solution has a very distinct pale purple color, whereas our diol over here is colorless. So as it reacts and as we reduce the concentration of the pale purple manganate solution, we will see a color change into colorless, implying that we have a reaction occurring. This would then be able to be used to determine that we've got an unsaturated compound, because this reaction would not be able to occur with a saturated hydrocarbon if we had an alkane as opposed to our alkene. This isn't as commonly used as the addition reaction with bromine that we looked at last time, but still one worth noting and being aware of. Decolorization of bromine is more common. So now let's look at our harsh conditions where we've got hot and concentrated as opposed to cold and dilute, hot and concentrated. Same acidified manganate, that's our oxidizing agent's the same. We just got hot and concentrated, harsh conditions. So in this instance, we do have sufficient reaction conditions to sever the carbon double bond carbon. And our products will depend on what kind of alkene we have. So we do initially form the diol, however, we then get further oxidation depending on how many carbon chains are attached to the carbons of the alkene. So we get the initial formation of the diol that we saw before, but then the oxidation continues and we get a few different possible products is the word I'm looking for there. So if we've got no carbons attached, we would get carbon dioxide forming. So if I have a alkene, and let's just focus on this bad boy there, right? So we got no carbons attached. We just have the H, and then we have, you know, whatever we have on that side. We're not focusing on that side, we're focusing on this one. If I have my harsh conditions, I'm going to completely sever that bond. And what I'm going to do is this carbon is going to be forming carbon dioxide. So this carbon is gaining oxygen, we're oxidizing, we're breaking the alkene. This is with our hot, concentrated oxidizing agent. Then whatever this carbon will make will depend on whatever we are bonded to with these two groups. So if we have ethene, then both carbons will be converted to the carbon dioxide. Now, obviously, I haven't included all my reactants there. I'm just doing this generally to show us what we would form in this case. So no carbons attached to the carbon in the double bond. In the alkene, we will get carbon dioxide. However, if we do have a carbon attached, we will get different products. If we have one carbon attached, an aldehyde forms that is then further oxidized to a carboxylic acid. Let's have a look at this one. So let's say if we focus on this carbon again, only in this time I have a alkyl group, whatever that R is. Only one of them though. What we'll do is we'll first form the diol, and then we won't worry about that one. That's just, fill in the blanks there, whatever is in there. We first form the diol, but then we'll sever the bond, and I'll just make this a bit neater there. And our carbon here will first form the aldehyde, which is a molecule that looks like that. And then the R there. In fact, I might draw this slightly different. Let's keep it the same orientation that I have it here so we don't get confused. So we oxidize to the aldehyde, which is that group where we have a double bond O with a H at the end of the molecule. But then we can get further oxidation, which will convert it all the way through to the carboxylic acid. Like that. And then, my goodness, my board work is not up to scratch today, which will go all the way to the carboxylic acid there. So that's if we got one alkyl group that is attached to our alkene. Now again, what this carbon forms will depend on what is attached here. If it's got two hydrogens there, then we'll get carbon dioxide as well, because that is a carbon that is attached to only the carbon in the double bond. If we've got one carbon, we'll get another aldehyde, and if we have two carbons, then we will get a ketone forming. A ketone being a carbonyl that is in the carbon chain, as opposed to our aldehydes and carboxylic acids that have them at the end of the carbon chain. So let me draw that for you here as I make some space on the board. So again, just focusing on this left-hand side carbon. In this case, we've got two alkyl groups attached, R1 and R2, and then we've got a carbon, and then whatever this bad boy has, we're not focusing on that right now. Same thing, we'll get the initial oxidation to the diol, then we'll get further oxidation where we sever that, and this can form a carbonyl. I'll keep the orientation consistent. The carbonyl, and because we have two carbon chains attached to it, then we will have the ketone. We can't make the carboxylic acid because of these two alkyl groups that are attached to it there. So again, this is coming from that carbon. Whatever the products of this carbon is will depend on what it's bonded to. If we've got two hydrogens there, this will make carbon dioxide. If we've got one alkyl group, we'll make an aldehyde, then a carboxylic acid. And if this also has two carbon alkyl groups, we'll make another kind of ketone. Could be a different ketone if they're different groups, could be the same ketone if they are the same groups. So a few different products there depending on how many carbons attached. But the thing to bear in mind is that we are severing the bond with the harsh, hot, concentrated conditions. The cold, dilute conditions, we can't sever the bond, we just form the diol. Harsh conditions, we first form the diol, then we sever the bond, and depending on how many alkyl groups, depends on the kind of carbonyl product that we will make. So to reiterate, no carbons attached to it, CO2 is formed, one carbon attached to it, an aldehyde, which is then further oxidized to the carboxylic acid. Two carbons attached, we form the ketone. Here's a task. Use what we have discussed about oxidation with, I think that's meant to say with, cold dilute and hot concentrated to fill in this table. So, fill in the blanks. Consider what are the reaction conditions. Remember, hot concentrated severing the bond, cold dilute forming the diol. Consider what the product is here, and then consider what the alkene will need to be there. Give that a go, pause, draw the table, fill it in, and we will check when you are done. Okay, let me first talk you through it. So we got hot concentrated. So we are going to be severing that bond. Ethene has no other carbon groups attached to our alkene, so we'll get two carbon dioxides there. We're forming the diol. We have the unharsh conditions, so we have cold dilute. Forming the diol, we're going to have cold dilute and eth, we're going to have an ethene. And then the middle one here, we're going to have the propene because we're forming the carbon dioxide at one end and the ethanol at the other end. In fact, that third one I might draw up so that we can have a look at why we get that. So let me go through this one here in particular. Propene. I've got C, double bond C, like that. Put my hydrogens in, if I can enunciate my words correctly. Now let's consider we have harsh conditions, hot concentrated. So we're severing that bond. So we're breaking that bond. We have a carbon with no other carbon groups that are attached. So if I go back here, no carbons attached, we form the carbon dioxide. And then we have the carbon that has one carbon attached. If we have one carbon detached, then we'll form the aldehyde, and that could also be further oxidized to carboxylic acid. So CO2 plus ethanol, you could also say CO2 plus ethanoic acid would also be appropriate, assuming we have excess. Let me draw that. So we form, I mean, this isn't a proper reaction by any means, I'm just sort of showing the products. In fact, I won't even do a reaction arrow, let's just go products so we can get around this on a technicality. So CO2 from that one with no carbons attached to it, and then we form first the aldehyde from, that would look like this. So ethanol, and then that could be further oxidized into ethanoic acid. So if you put ethanoic acid there, all good as well. Excellent. Moving on to the second part of the lesson, once I read this final sentence, I can use the characteristic reactions to identify the position of the double bond in a larger alkene, identify the products of the oxidation, and retroactively determine the reactants. So based on the products you form, you can retroactively determine what kind of structure and what kind of double bond you have present. The final kind of alkene reaction we are looking at is something called addition polymerization. So we're adding two things and we're doing this thing called polymerizing that we haven't seen this phrase before. Alkenes are in such demand due to their use in the synthesis of plastics. So these polymers that we make are essentially plastics. So I'm going to sort of use plastics and polymers synonymously here. You do have different kinds of polymers. You've got like biological polymers, but I'm just focusing on these addition polymerizations, which is what we use to make our plastics. Now, I don't need to convince you the usefulness and the prevalence of plastics. I mean, just look in your immediate vicinity and count how many things have plastic in their structures. Also think about how many times you use plastic bags or, you know, plastic packaging. It is a lot. They are everywhere and they have excellent uses, but there's also negative ramifications as well. Countless applications of plastics. So plastics are a type of polymer synthesized through polymerization reactions of monomers. So let's break down these words as we often do to understand them. Mono is a prefix that means single, as in a monocycle has a single wheel, a monocle has a single lens. Poly, on the other hand, is an ancient Greek word that means many. For example, compare a monotheistic religion, which has one god, with a polytheistic religion that has many gods. So mono one, poly many. And then mer is ancient Greek for part. So monomer is one part, polymer is many parts. And this makes sense. We make many parts from one parts, and these parts are our molecules. Polymers are large chain macromolecules that are made up of many repeating units called monomers. Many unsaturated compounds, such as ethene, can undergo addition polymerization. Consider the polymerization of ethene itself. Let's consider we have two ethene molecules. Am I going for space? Good. And I add these together in addition reaction. So I get the two reactants and I make them one product. So let's say I react them together, I open up that double bond and I form a new bond between these two carbons. I would get something that would look a little bit like this. Like that. So I've opened up that double bond, formed a new sigma bond between the two carbons, and we now have something along the lines of that. Let's say we let's say we pick up a hydrogen somewhere along the way just for the ease of my storytelling here. So now let's say that we get another ethene, which I'll draw down here. And let's say that we react that with the end of the molecule that we made here. And I would extend that carbon chain even longer again, wouldn't I? I would have another 2 carbons. Let's say I react it with another ethene, I get another 2 carbons, so on and so forth. We can simplify this by having our ethene molecule. The number of ethene is just N. N can mean any number. Could mean 2, could mean 2 million. And then we form this repeating structure that is our polymer made up of many parts from our one part. So if I were to draw the diagram to represent this general equation, it would look something like this. I have N number of ethenes. And what I form is I form a N amount of this repeating unit that looks like this. So brackets, like in maths, everything in brackets applies to this N. So however many of these I react together, I will get that amount in a row repeating again and again like this, like we just saw with my example with 2, then 3, then 4, then 5, so on. So this is our polymer from our monomer. This is our many parts from our single parts. Okay, what do I have here? Polymerization is a type of addition reaction where atoms are adding across the pi bond of the alkene. The repeat unit of a polyalkene, so many alkenes from a monoalkene, I suppose, or just an alkene, is the same as the monomer, only without the double bond. So essentially, you're just converting your alkene into an alkane. Exactly the same, we got the same things coming off. If we were to make this a little bit more complicated, let's say my monomer had a chloro there, it would be the same up here, only instead of having the double bond, we got the single bond. So it's just whatever your repeating unit is, repeated many, many times. Note, the name remains polyalkene, for example, polychlorethene or polyethene, as I got over here. Despite technically being an alkane, if it's made from ethene, well now this is chloroethene, this would be polychloroethene. Even though it's an alkane, the name comes from what you're saying the many parts were. Hopefully that makes sense. Okay, 2 things we need to be able to do when we have a polymer type question. The first is to be able to identify what our repeating unit is when given the monomer, so working out our polymer when given the monomer, or determining what our monomer is when given the repeating unit, so doing the vice versa, working out what the monomer was from the polymer. When we are given the monomer, we just have to turn the double bond out, essentially show the same thing just with a single bond between them, turn those bonds out of brackets, and then just bracket the repeating unit with N amount. All right, let me read this to make a bit more sense there. We change the double bond into a single bond and show the bonds either side of the carbon atoms that would continue the chain. Put brackets around the repeating unit with N. For example, why don't you have a go at this based on the diagram that I just drew before? If we have, well, this is the exact one that I just did before, so hopefully you're paying attention. If we have this chloroethene, and that's our monomer, what would the repeat unit look like? It would look like this. We turn the double bond into a single bond, and then we turn a bond out to show that these keep bonding with subsequent units, bracket our repeating pattern, and then put an N down there to say that this repeats as many times as we had these over here. Conversely, determine the monomer when given the repeat unit of the polymer. Same but different. We identify the repeating unit and then we do the opposite. We place the double bond inside the brackets, specify the N before the monomer. For example, if we had this repeat unit, what would the monomer look like? Pause, have a go, and check the answer now. Well, we put the double bond between them, and then we just place the N before. So if we had the repeating unit that looks like this, if I draw it out, what have we got? We got a phenyl group. Am I going for space? All good. And then we got a methyl down the bottom there. So if this is my monomer, so it's saying we're repeating this n amount of times. Then my monomer from this, I've just got to turn the double bond inwards like that, and we will get the monomer that looks like this. So this is our single part that makes that many part, and we will have n amount of that. Again, n unknown is just as many as we specify depending on our reaction. So there is an introduction to polymerization reaction. Now we can make these very, very useful plastics that have a multitude of uses, from innumerable amount of uses, from packaging and bags and buckets, ropes, carpets, insulation, piping, non-stick coatings. You can go on and on and on. Like I say, just think about how many plastic things you have used today. However, there are negative consequences from how much we have incorporated plastic into our lifestyle. But also note there's other kinds of polymers such as condensation and biological polymers that we're not focusing on right now. We're just looking at our addition reactions. They are incredibly durable and incredibly inert. I mean, they are just alkane molecules, and we've looked at how unreactive alkanes are. And whilst this is very good for some of the uses, it means they're going to last for a very, 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 very long time, and they're difficult to dispose of. Let's consider this non-biodegradability. So we can consider plastics as massive alkane molecules, and we've seen previously just how unreactive alkanes are. So that means it takes hundreds or even thousands of years to decompose, because that's how things decompose from chemical reactions. And we're using these plastics, these things that stay around for a very, very long time, for uses that we just immediately dispose of. Think about getting food in a packaging, and we take it out of the package, we immediately throw it in a bin, think that it's going to go away, but in actuality that's not going to go anywhere for a very long time. It's going to sit in a landfill or make its way into an ocean. But it's not as simple as saying banning all plastics is a negative thing, because those plastics have excellent uses. I mean, think about how long we can keep perishable food fresh for, where without those plastics we wouldn't be able to preserve that food like that. So I'm not saying it's as easy as just not using plastics anymore, but we can sort of ethically and consciously consider our plastic intake in our everyday lives to help conserve the environment and reduce some of these pollution factors. So pollute the environment, especially the oceans. They all, if they get into any river source, most river sources, or water source rather, will find its way back to the ocean, and that will affect the marine life and all sorts of knock-on effects for a very, very long time due to this inertness. And there's this current issue that has only recently come to light of microplastics. And these are plastics that are smaller than 5 millimeters. So although our alkanes are very unreactive, they can be decomposed by UV radiation. So you imagine plastic floating in an ocean, getting all that UV rays, it will eventually react and start to decompose. However, it is going to get into the food cycle of the marine life. Small marine life will then consume it. I mean, these are very small pieces of plastic, but small marine life can consume it, and this can then make its way up the food chain and eventually get to us. Now, there's potential health risks that could be associated with this, but the sort of perturbing thing is that there's just lots of unknowns about what these microplastics can have for our health. Now let's talk about how to dispose of. Burning plastic waste. We've talked before about the idea that hydrocarbons can be burnt to get lots of energy, the very exothermic reactions, and we can harness that energy for lots of uses. So you might think, well, can we just burn these plastics and then harness the energy? 2 birds with 1 stone. However, we've also discussed the pollutants. We will get a mass amount of carbon dioxide as a greenhouse gas and highly toxic carbon monoxide. These, carbon dioxide as a greenhouse gas will contribute to climate change that is real, that is occurring, and that is human influenced. So we can't burn these because of the pollution with those effects. Also, carbon monoxide, highly toxic, not something we want to be inhaling. If they contain other atoms as well, we can get a number of other nasty byproducts. For example, we had our chloroethene polymer. If we've got chlorine atoms, we can make hydrochloric acid gas. Again, not something that we want to be breathing or releasing into our environment. When it comes to plastic waste and pollution, the best course of action really is recycling. The durability of plastics makes them reusable and recyclable, some plastics more than others. So that means that we can repurpose and recycle and reuse plastics for other jobs once their initial job has finished. But this is by no means a flawless process. I mean, there's got to be infrastructure to collect and to sort and to, refashion the plastic, and that's going to have all its own pollutive or non-pollutive knock-on effects as well. So by no means is it a dichotomous issue. There's not a right answer and a wrong answer here. We've got to consider all sorts of knock-on effects that just changing one variable will have. But by considering all the pros and the cons, hopefully we can ethically, as a species, find a way to reduce the pollution while still enjoying the benefits of the lifestyles that we currently have. Really, when it comes to plastic waste, reduction is the best approach, considering how you can reduce your plastic use both in your personal life and also, as we scale it up to massive industries and massive organizations and those kinds of things. Ethically reducing the amount of plastic might be the best course of action. And with that, we finish both our lesson today and also our unit on hydrocarbons. What have we done? We've described the chemistry of alkenes as exemplified where relevant by the following reactions of ethene and propene. We looked today at oxidation by cold dilute and hot concentrated acidified manganate to get different products. Cold dilute, we form the diol. Hot concentrate will rupture the carbon-carbon bond, and we can use whatever products we get to determine the position of alkene linkages in large molecules. And then we discussed polymerization. Describe the characteristics of addition polymerization as exemplified by polyethene and PVC. Deduce the repeat unit of an addition polymer obtained given a monomer. Identify the monomers present in a given section of an addition polymer molecule. Recognize the difficulty of the disposal of polyalkanes, the non-biodegradability, and harmful combustion products. You beauty, we got through it. Here are the tasks for the lesson. Pause now, work through it, and you will consolidate your understanding of the content we've looked at. Very well done. Thanks for your time. I'll see you as we start our next unit in the next video. Have a fab day. Bye-bye.